Good morning. So today in this video we are going to learn about the standard electrode potential. Okay. Now what is a standard electrode potential? Before we give the definition, let's try to understand. It is basically given to a metal with its corresponding solution. I mean to say the metal electrode with its corresponding salt solution. Because whenever we keep a metal electrode in its salt solution, there exists a potential difference. And that potential difference is what we refer to as the standard electrode potential. Now, the word standard means whenever we say, if we are talking in general about electrode potential, it means metal with metal ions of any concentration. But when we put the standard before it, what it means is the concentration of the solution should be approximately 1 molar. Okay, so when we have a metal electrode dipped in a metal ion solution, its corresponding metal ion solution of 1 molar concentration, in that case, the electrode potential that we observe for this system is referred to as the standard electrode potential. Okay, and usually we when how we measure the standard electrode potential, because there is no way we can calculate the potential existing between the metal and its solution by connecting a voltmeter. So we need a chemical battery to really find out the potential that is here existing. Okay, so in order to measure that, what we use is we connect this system of metal and its corresponding solution to another system, which is our reference electrode. In this case, there are many kinds of reference electrode which you will be learning in your physical chemistry. One of the reference electrode that we use is standard hydrogen electrode. Okay, so basic diagram I'll tell you. It is basically a Daniel cell. Okay, so we have the metal electrode dipped in the corresponding metal ion solution. Since we are trying to measure the standard electrode potential, the concentration of the metal ion solution is 1 molar. Then this is connected to the standard hydrogen electrode. Now, what is a standard hydrogen electrode? Basically, we have a platinum electrode dipped in H plus ion solution, again 1 molar concentration, and through this solution we bubble H2 gas at 1 atmosphere pressure. Okay, so basically this is what is a standard hydrogen electrode. Hydrogen at 1 molar atmosphere, 1 atmosphere, and the hydrogen ion concentration at 1 molar. So this is the basic setup of the standard hydrogen electrode, and we connect it to uh, our metal and its solution in order to calculate the standard electrode potential. So basically, this is connected via a wire. We have a voltmeter here. We have a switch. And then in order to complete the circuit, we will use a salt bridge to connect the electrolyte solution. Okay, this particular thing you already have learned in your lower classes, how to what this chemical battery involve. Okay, so this is the setup that we use in order to calculate the standard hydrogen electrode. Now, when we connect the system and we switch it on, whatever voltage you get here, that is corresponding to the standard electrode potential, because in this setup, this electrode potential that we have here is always taken to be 0 volt. Okay, so this half reaction, whatever half reaction is happening in this part of the electrode, is taken to be 0 volt. Then whatever voltage you obtain here is the voltage corresponding to this electrode. So this is how you measure the standard hydrogen electrode. Okay, let us see an example. So here you can see we have a zinc ion system. Okay, so when you connect it, and usually when we take the setup, the standard hydrogen electrode is taken to be the cathode, and the other electrode of which we are measuring the electrode potential, we take it as the anode. Okay, uh, but it depends. Okay, depending upon whether it's a reduction reaction happening here or an oxidation reaction happening, um, the actual can be reversed. But usually when we measure, we take the standard hydrogen electrode to be cathode and the metal and its ion solution at the as the anode. Okay, so in this case, when we connect the zinc ion system, the voltmeter gives a reading of 0.76 volt. Okay, so 0.76 volt. So if we try to measure, this is a cell. Okay, so E naught cell, if we try to measure, we know that it is always E cathode minus E naught anode. E cathode in this case, always remember these values are reduction potential. So basically we are uh, take for this half electrode, we will take E naught H plus H2. This is the reduction reaction, so that's why we write it as H plus H2. And the other side, it is zinc, so it is zinc 2 plus zinc. Okay, so these are basically the reduction potential. Okay, so now let us put the values. So E cell, okay, E cell that you obtained here is 0.76 volt. That is what you got from the voltmeter. Okay, and E cathode here, which is this standard hydrogen electrode, I just now told you, we take the reduction potential value for the standard hydrogen electrode to be 0. Okay, so if that is the case, if this is 0, in order to get a positive value, the reduction potential for this system should be minus 0.76. Okay, so that means the E naught value for the standard reduction potential or the standard electrode potential for the zinc system is basically minus 0.76 volt. Okay, so that is what it means. So this is the standard electrode potential for the zinc system. Okay, let us look into another example. This is an example of copper system, copper with its corresponding ions. Okay, now here if you look carefully, the voltmeter shows a negative value, that is minus 0.34 volt. Okay, keeping the system as anode and cathode, what we obtain here is E naught cell, which is again hydrogen minus the copper system. Okay, now this we know to be equals to 0. Okay, in order to get a negative E cell, obviously the reduction potential value is positive. Okay, so now the standard electrode potential for a copper system, that is copper 2 plus to copper, is basically equals to 0.36 volt. Okay, so this is how you measure the standard electrode potential for various metal electrodes. Okay, so this is about the measurement. Let's now try to define what is a standard electrode potential. Now, if you look carefully at this definition, the standard electrode potential of metal with respect to its metal ion solution is defined as the reduction potential. Always remember, the standard electrode potential is referred to as the reduction potential. So it's defined as the reduction potential obtained against the standard hydrogen electrode, provided the concentration of the metal ion solution is unity. So that is what I was telling you. Whenever you are talking about a metal electrode dipped in its solution, the concentration of the metal ion solution should be unity or 1 molar. Okay, provided that condition is obeyed, whatever potential you get from this Daniell cell is what you refer to as the standard electrode potential. Okay, so this is how you can define a standard electrode potential. Now, how it is useful, let us try to understand some of its applications. Now, when it comes to the E naught values, okay, if we have a negative E naught value, what it signifies is it's a reducing agent. For example, in the example that we just now discussed, we talked about the E naught value for the zinc 2 plus zinc system, and it was basically minus 0.76 volt. Okay, so this was the value. So this means this system, this electrode is actually, this system is a good reducing agent. So that means zinc metal, okay, is a very good reducing agent, and that is why when you treat zinc with H plus, it will always liberate hydrogen ion by converting to zinc 2 plus plus H2. So it will always liberate the hydrogen. Okay, so that is because zinc is a very good what you see reducing agent. So that is what you have to keep in mind. Okay, so and if it is a positive value, then that means it's a good oxidizing agent. It won't be able to displace hydrogen from its solution. Okay, and thus the E naught value is very useful in order to understand the direction of reactions, especially involving redox reactions. Okay, and you have already learned and you know the table which shows a electrochemical series where you have different metal with its metal ion solution. You have a standard electrode potential given in a table format in which elements are arranged in the increasing order of their electrode potential, and that table is referred to as the electrochemical series. So all those metals who have a negative value would be good reducing agent, and they would be able to displace hydrogen from the solution, and those having standard hydrogen electrode having a positive value in comparison to the standard hydrogen electrode, those will not be able to displace hydrogen ion from the solution. Okay, so such metal, for example copper, it has a negative it has a positive value. Okay, positive value. So positive electrode potential, mm, because it's a positive electrode potential, it won't be able to displace the hydrogen. That what I mean to say is, if you react copper with H plus, there would be no reaction happening because copper won't be able to displace hydrogen because of its positive reduction potential value. So it prefers to be a good oxidizing agent. Okay, so these are some of the good applications of the E naught value. Let us now try to compare the various elements and try to understand how the E naught value varies in different groups in the periodic table. Let's first start with the alkali metals. Now, if you look at the alkali metals here, the values, what you see is what we expect is the E naught value to be negative, and it should increase in the downward direction. That means the negative E naught value should increase down the group because the ionization energy decreases down the group. So we expect these to show a negative value, but the negative value increases down the group. But what you see here is there is a not very smooth increase in the E naught value. The values are negative, but the increase is not very smooth. Okay, so that means there is something which we are not trying to take into consideration. For example, if you see the value of lithium, it should be the lowest. It should be actually positive value because lithium has a very high ionization energy because of its small size. Okay, and because it has a very high ionization energy, we expect it to be rather a good oxidizing agent than being a reducing agent. But the value of E naught, which is highly negative here, shows that this is a very good reducing agent. Okay, so how to explain uh, these drastic differences? Okay, so in order to understand that, we have to understand the half reactions. Okay, so if you look at this particular half reaction, for E naught, when you talk about the half reaction is basically the metal ion in the aqueous state. Okay, it combines with electrons to give the metal solid. This is the half reaction that you talk when you calculate the E naught. Okay, now here what you see is you have a aqueous changing to metal solid. Okay, but if you remember the ionization energy is basically M gas. Okay, uh, turning to Mn plus gas plus electron. So before that, solid need to undergo sublimation to form the gas, and then the gas undergo ionization to form the Mn plus gas, and then gas then undergo hydration to form the Mn plus aqueous. So all these things you need to consider in order to get to this particular equation. So that means the E naught value is dependent upon the sublimation, ionization energy as well as the hydration energy. Okay, so why we don't see a very smooth increase while we go from lithium to cesium is because we here there is a good variation, though the ionization is smoothly decreasing down the group, but there is a there is a drastic change that you observe in the sublimation as well as the hydration energy, which is causing the uh, non-smooth increase of the E naught as you go down the alkali group. Okay, now why in lithium we have a very high negative value? That is because in case of lithium, the hydration energy is highly negative. Now, why the hydration energy is highly negative? Because lithium is a very small atom, so it has a very high charge density. Okay, so because it has a very high charge density, it is hydrated because of the high charge density. It is hydrated maximum. It is hydrated to the maximum. Okay, so it is hydrated, and that's why it has a very high hydration energy, and this hydration energy decreases when the metal ion size increase. So if the size of the ion increases, the hydration decreases because the charge density, charge to radius ratio is in decreasing as you move down the group. However, in case of lithium being small size, the charge to radius ratio is very high, and that's why we have a very high hydration energy. And that is why, because of the high negative hydration energy, the E naught value is highly negative in the case of lithium. Okay, so that is what I've written here. The high hydration energy of the lithium ion is responsible for the high negative E naught value, and that is why lithium ion is the stronger reducing agent among the different alkali metal. We expect cesium to be a stronger reducing agent because it has a lower ionization energy, but lithium is the strongest reducing agent, even though it has a very high ionization energy, and that is mainly because of the high hydration energy that you see in the case of lithium ion because of the high charge to radius ratio. So here we see a very high uh, charge to radius ratio. Okay, because of the high charge to radius ratio, it is hydrated very strongly, and that is why it has a very high negative E naught value. Okay. Now, when we talk about alkaline earth metals, the alkaline earth metals, if you look at the values, it's given in your books. What you see is the negative, it is also having a negative E naught value. That means they are good, what do you say, reducing agent, but the negative value is of a lower magnitude than the alkali metals, and that is why alkali metal is more stronger reducing agent than the alkaline earth metals. Okay. Now, in that case, or in their case also, when we talk about beryllium, okay, beryllium also shows a negative value there, 1.9 volt. If I remember correctly, in the case of alkaline metal, beryllium also shows a value of minus 1.9 volt. Okay, and we like lithium, we expect a positive E naught value here because beryllium being smaller in size, we have a very high ionization energy, so we expect it to be a oxidizing agent rather be a reducing agent. But here we see a negative value, again the same reason, because of its small high charge to radius ratio, it has a very high hydration energy. That is why in case of beryllium also we are getting a negative E naught value. Okay. Now let us look into the p block elements. P block elements. So this is the group 30. So this is group 30. So if you talk about the reduction of M3 plus to M in these elements from aluminium, gallium, indium, thallium, what you see is the plus 3 oxidation state is kind of becoming less and less stable as you go down the group. And in case of thallium, it is showing a plus electrode E naught value. So that means the reduction is uh, highly possible. Reduction is highly possible. So that means the plus 3 oxidation is highly unstable when it comes to thallium. And except aluminium, when you go to gallium, indium, the stability of the plus 3 oxidation is decreasing because you can see the negative value is decreasing down the group. Now, why do you see such a shift or such instability of the plus 3 oxidation state as you go down the group? Because you expect the negative value to increase as you go down the group because the metallic character increases down the group. But still, what you see here is the negative value is decreasing and it's almost becoming positive in the case of thallium. Now, to explain this, we need to understand what you call it as the inert pair effect. Okay, this is because those elements that are coming post transition elements, for example, when it comes to gallium, indium, they are coming after the D block elements. And thallium, if you talk about, they are coming after the F block elements. Okay, so because they are coming after the D block and the F block elements, the we know that the D subshells and the F completely filled D subshells as well as the completely filled F shell subshells. They have a very poor shielding effect. Okay, and because they have a very poor shielding effect, they are not able to what you say stop the nuclear charge effect of the nuclear charge. As a result, what happens, because if you talk about the configuration in group 13 element, it is basically ns2 np1. So as you uh, go down so as you go down the group, that is gallium, indium, thallium, because of the involvement of filled D and the F subshell, which have a very poor screening effect. What I'm saying is they have a very poor screening effect. When I say poor screening effect, what it screens is it screens the nuclear charge. So being a very poor screening effect, the nuclear attraction is felt very strongly, especially for this ns electron. As a result, what happens, these are very closely bound to the atom, and thus the plus 3 oxidation state is highly unstable as you go from gallium to indium to thallium. Okay. However, plus 1 oxidation state is more kind of favored. Okay. For example, if you are talking about the reduction of M3 plus to M plus, M3 plus to M plus, uh, you will see a kind of positive value when you move from gallium, indium, thallium. In thallium case, you will see more positive value for this reduction because of the inert pair effect. Plus one oxidation state becomes more stable as you go down the group, because here the D subshells and the F subshells, they poorly screen the nuclear charge, and as a result the ns electrons are very tightly bound and therefore not very reluctant to undergo any kind of ionization energy. And that is why you see a decrease in the negative value as you go down the group in the case of group 13 element. This you find even in the group 14 elements. If you see here, group 14 element, uh, where the this is group 14, and we know the electronic configuration is generally ns2 np2. Okay, so if you talk about the reduction of m4 plus to m2 plus, what you see here is as you go down from stannous to plumbum, it is having a positive value. That means this reduction is highly favored. That is again because of the inert pair effect. That means plus 2 oxidation state is highly stable um, when you go down the group in the case of group 14, because we know group 14 involved carbon, silicon, germanium. Okay, so when you talk about these group, down the group, we expect that down the group it should be highly negative because metallic character increases. But here we see it becomes positive, and that is because of the inert pair effect, because of the reluctance of the ns electron to participate in oxidation. Okay, and that is why here also when you talk about m2 plus to m plus m reduction also, they are showing a lesser degree of, though it's a negative value, but as you go down the group it is showing a reluctance to undergo reduction. Okay, that again shows that the plus 2 oxidation state is highly stable. From the E naught value we understand that, and the reason for that is the inert pair effect. In group 13 it is the plus 1 oxidation state that is favored. In group 14 it is the plus 2 oxidation state that is favored. Okay, so before we wind up, let us talk about the definition of the what do you say, the inert pair effect. So you can see here, inert pair effect is the tendency of the two electrons in the outermost s orbital, atomic s orbital, to remain unshared in compounds of post transition metals. Okay, So that means the reluctance of the two electrons of the ns electrons, okay, that is atomic s orbital electrons to participate in any kind of bonding, okay, that reluctance is what we refer to as the inert pair effect, and this is observed only in post transition metals. So that means all those elements that are coming after the d block and the f block element, you experience this phenomena of inert pair effect. The term inert pair effect is often used in relation to increasing stability of the oxidation state that are 2 less than the group valency for heavier elements. So uh, if the group valency is +3 in the case of group 13, so the increasing stability of the oxidation state that is 2 less than, that means 2 less than 3 means +1 oxidation state. In case of group 4, 2 less than means it is +2 oxidation state. So that oxidation state becoming more stable, okay, that is what we refer to in the inert pair effect, and this is basically observed in heavier elements of group 13, group 14, group 15 and group 16. Okay, so that is about the inert pair effect. Now why this inert pair effect happen? As I told you, it is again because of the completely filled D and F subshells, because of which what happens, there is poor screening effect of the screening of the nuclear charge. As a result, the nuclear charge is very much felt by the valence electron. As a result, the ns electrons are very tightly held to the atom, so the np electrons are only participating in the oxidation. Okay, so that is why we see this inert pair effect phenomenon. Okay, so I hope you understood the standard electrode potential and the variation in various S and P block elements. You can refer to the books, it's there. You can just read through it. Okay, and if you have any clarification, please let me know. So that's all for today. Thank you.